Hello, everyone. I am Safillah and I am an assistant professor at Manchester Metropolitan University in Manchester, United Kingdom. And today I am going to talk about post-quantum cryptography, what is the current status of PQC, and what are the emerging research directions. In my talk, I will be quickly reviewing about what PQC is, what are the current status. I will talk about this standardization process of some of the PQC algorithms. I will highlight my research and the research that I am currently doing in this domain. Starting from what cryptography is, or what is the traditional cryptography that we use today. So it is actually the established methods for securing our data and communication. The cryptography that we use actually relies on some of the hard problems and keys to encrypt our data. For example, we have RSA and elliptic curves, which belong to the family of asymmetric cryptographic algorithms. We have AES, which is a symmetric version of cryptographic algorithms. We already know that with the rise of quantum computers, there is a threat to the cryptographic algorithms that we use today. And the reason is that the quantum computers basically utilize quantum mechanics to perform computations that are way faster than the computations we can perform with the classical computers today. This is somehow a threat to the traditional cryptographic algorithms because of quantum algorithms like Shor's and Grover's algorithm. So the Shor's algorithm basically states that it has the capability to factorize large integers, and this is the hard problem upon which RSA relies on. If you can somehow factor large integers with a quantum computer, this means that RSA will be broken. The same is true for discrete log problems as well. On the other hand, the Grover algorithm somehow reduces the security of the symmetric cryptographic algorithms by halving the effective key length. This means that once we have quantum computers, we need probably double the key size of what the keys we are using for the symmetric versions of cryptography. In short, what is the implications to cryptography? The cryptography is vulnerable to quantum threats. The publicly cryptographic algorithms are vulnerable to Shor's algorithm. There is no mitigation available except designing new cryptographic algorithms with hard problems that are even resistant to the quantum threats. For the symmetric version of cryptography, this is vulnerable to Grover's algorithm, but the mitigation is increasing the key sizes. There is an urgent demand for post-quantum cryptography, which means that the algorithms that can withstand the quantum attacks as well. So the aim of PQC is to ensure the security of the data transmission, even in the era of quantum computers. Somehow, formal definition of what PQC is. So it refers to the cryptographic algorithms designed to resist the attacks from the quantum computers. There are a number of objectives of moving towards PQC. The first one is to deploy cryptographic algorithms that gives us security in quantum era. It ensures the long-term security of the sensitive data and communication channels. It's not just about designing algorithm, it's about facilitating the transition from what we use today, which are the traditional cryptographic algorithms, to the newer versions of cryptographic algorithms in the coming times. So what is the current status of PQC at the moment? So researchers have identified some of the hard problems that think they are resistant to quantum attacks. Here are some of the cryptographic algorithms' hard problems. So the most famous among them is lattices-based problems. Most of the algorithms from the PQC domains right now are dependent on the hard problems that are lattices-based. We have some standards from hash-based and code-based as well. So in short, we do have some hard problems upon which the modern or the post-quantum cryptography is designed upon. NIST actually started a standardization process for PQC, and last year NIST published its first standards. So there are 4 algorithms that were published last year to be selected for as standards. The first one is ML-Chem, previously known as 𝗤𝗺𝗫, which is a key encapsulation mechanism. We have 3 digital signatures algorithms, crystals, dilithium, Sphinx, and Falcon, which were selected to be standard NIST standards for post-quantum digital signatures. This year, we have a new standard, which is 𝗥𝗚𝗃, which is based on code-based key encapsulation mechanism. This is to diversify the CHEM portfolio, because if you look at the first four algorithms, including the key encapsulation and digital signatures, 3 of them were based on lattices, and NIST actually wanted to diversify the portfolio by introducing algorithms that are based on problems other than lattices. That's why we have a new standard 𝗥𝗚𝗃 this year. What is the point of view from different governments and the regulatory bodies? So NSA in the US has provided its guidelines for related to migration as well, and it has given a transition window as well. So from the year 2025 to 2030, all the algorithms that we use will be phased out. And then from 2030 onwards, in US, they have actually mandated to use the post-quantum cryptography. Similarly, here in the UK, the National Cybersecurity Center has published its own migration timelines. It's a phased strategy here where we are currently identifying the areas which are most vulnerable to quantum computers, for example, the health domain, the military communication. Regulators are basically emphasizing at the moment towards the hybrid deployments where we can use classical and post-quantum cryptographic algorithms together. This is to enhance a smooth transition period from one schemes to the other schemes. They're also prioritizing data that needs long-term confidentiality requirements. Industry has somehow adopted PQC as well. If you look at Cloudflare, major browsers, Chrome, Firefox, or other cloud providers, they have included PQC into the TLS domain. So now they are using Kyber, which is MLChem now, along with some other algorithms, for example, 𝗥25519, which is a key exchange algorithm based on elliptic curves. So with this, they have somehow come up with the hybrid TLS, including the post-quantum algorithms as well. This doesn't come free. Definitely, it has some practical consequences. The key sizes for the newer algorithms are large. The signature size are larger. You need to update hardware security modules, and they are also prone to side channel resistances. So there are lots and lots of challenges when it comes to implementation and practical deployments. In the short term, what we are looking at, definitely we are looking at hybrid CHEMs, for example, a hybrid solution combining both PQC and the traditional cryptography, update the TLS stack, update the HSM firmware signing positions. So this is something that we are doing in the meantime before fully moving towards the post-quantum algorithms. We can find applications of PQC everywhere. Blockchains, once again, depend heavily on hashing and digital signatures. Similarly, the government and military communication, or the sensitive information which we are currently encrypting with traditional ones, have to move towards the PQC. There are some implementation challenges, or we can say the current research directions. So the first one could be the performance considerations. The newer algorithms are computationally complex. They require efficient solutions for their implementations. They have a large key size, which means they require more bandwidth. The integration with the existing systems is challenging. We are looking for standards that can interoperate with the traditional algorithms that we use today. So these are some of the challenges that we have while we are migrating towards these newer standards. I mostly work with the implementation side, so now I'll talk a little bit about my research. I've been working by implementing MLChem, which is known as crystals Kyber as well, which is a post-quantum key encapsulation mechanism, and it belongs to the family of lattice-based cryptography. The underlying problem for MLChem is module learning with errors, and which is somehow more superior to other schemes, for example, ring learning with error schemes. I mostly work on implementation with FPGA platforms. There are a number of implementations of PQC that we can find in literature, and my job is to implement and make these implementations very specific to certain applications. The applications that I have been mostly working with is in the domain of space missions, because there is an extra challenge introduced when we are implementing these algorithms for space missions. And the challenge is that since the FPGAs are based on SRAMs, so when they are prone to radiations, they actually introduce a single event upsets, which means that some of the bits are flipped due to the radiations. If there is a bit flip during encryption or decryption process, which means that the entire result will be completely different. If we have encrypted something which is erroneous, we cannot decrypt it back to the original plain text. So somehow we have to take care of this single event upsets as well. With one of my latest research, we have actually proposed an architecture to compute a polynomial multiplication, which is a major component of ML-Chem. And in order to compute polynomial multiplication, we are doing it through number theoretic transforms. So we have designed an architecture for entity with not just only compute entity, but can also detect and correct errors as well. We have implemented it on different FPGA platforms, and I will definitely show the results once I have discussed this. Inside this entity, one of the major component is a reduction unit, modular reduction unit. The modular reduction unit is designed using the Barrett algorithm. Since the mod value Q for Kyber is fixed, so that's why we have pre-computed some of the values. The multiplication involved is computed through schoolbook approach, and we design a Barrett reduction algorithm here. An architecture that is based on the Barrett reduction algorithm. Once we have this basic architecture here, which we can see here as a small box as mod, then we design the entire entity architecture. So number theoretic transform is basically a multiplication process where we take some coefficients of the polynomial, some trivial factors, and multiply together and store the results. So there are register banks here at the input and the output side, and then we multiply them, take the mod, store the results at the output here. So during the start of computation, the coefficients are first loaded into the registers, and then each clock cycle, 2 coefficients are read from the register banks, multiplied, and the output is stored in another bank of registers. And this happens sequentially. Once all the registers are stored in the register banks, the computation for the second layer starts, because there are a certain number of layers within the entity structure. So this is the basic architecture of entity. But what I do is somehow modify this architecture to introduce some capabilities where it can detect the errors and it can correct the errors itself. And for that, I have introduced some parity bits, some Hamming weights. So I compute some Hamming weights here, which are stored in the register instead of, along with the trivial factors, and then repeat all the computations here. So the architecture shown here basically introduce extra capabilities of error detection and correction as well. So we compute the Hamming weights for each trivial factor, and we only not just only save the Hamming weight, but we also saved it, not only just save the trivial factors, but also save their Hamming weights as well. So the butterfly core, which computes the entity, runs the same way, and inside the butterfly core, the Hamming codes are computed again and compared with the Hamming code that is received. If there is a bit flip, definitely they will not be the same, and the corrected output is then processed to the standard entity computations again. The same is true for the value of the coefficients that we store. We compute the parity for each of the coefficient that is being computed by entity. And if there is a bit flip in the computation, the parity bit indicates a bit flip. And if there is a bit flip, we just trigger the reset signals to do the computations all again. So this is the basic architecture that we have proposed in our work. When it comes to the results, I have computed the results on FPGA for the basic architecture, for the one where I have introduced the Hamming codes, and the other one where I have introduced Hamming codes plus parity bits. So the thing to be noted here is that there is some kind of percentage area overhead. Although we have increased the area, but the implementations that we have made are now more much more suitable for certain application, which is the space application in our case. So that was all about my talk. Thank you so much for listening. I have tried to introduce the concept of post-quantum cryptography, its implementation, standardization process, and the application that we are doing specifically in the space applications. Once again, I apologize, I couldn't make it to the live event. So if you have any questions, you can send me an email. I have put my email address here, and I will look forward to your emails if there are any questions. Thank you so much for your time.